introduction. So hello everyone, I'm Rubana. I have been a researcher with ThoughtWorks C4R team, and I primarily work in the FPGA domain. So yeah, this topic is pretty close to my heart. We would like to go on for our first talk of the day. Our first speaker is Dr. Shankar Selvaraj. He is with IISc Bangalore. Dr. Selvaraj's area of research includes high-speed integrated photonic devices, development of photonic materials, and device platform for on-chip photonic sensors. He has been actively involved for over a decade in the area of silicon photonics to develop state-of-the-art process and device technology for CMOS-compatible photonic integrated circuits for high-speed optical interconnects. Today, Dr. Selvaraj will share how integration of promising optic-based technologies with the traditional silicon architecture brings forth some very interesting and some even extraordinary possibilities in the future of compute fabric. The title of his talk is Merging Opportunities in Optics-Enabled Computing. So let's welcome Dr. Selvaraj. Over to you, please, sir.
All right, thank you very much for the introduction, Rubana, and the rest of the team here. It's a very interesting workshop that looks at, where we are and where to go. And, yesterday I couldn't join, but then when I heard about the different topics that Michael was talking about, that's what is happening in the world, going beyond Moore, right? It's beyond crunching more transistors. So the actual push of putting more transistors, right, was the primary drive towards meeting, or rather keeping the Moore trend go. But then that's not sustainable, right? There is a physical limitation for everything. And then, humans are smart. And we think a different way. We have to pat our back for that. But we need to look at clever ways of keeping up, not necessarily with the Moore, right? Since we don't have another fancy law or name towards it, though we can claim there are different claims around, but for all sanity, we just keep Moore, right? It actually appeals to a wider community that it is all about progression, right? So you're progressing towards something and progressing towards something better, right? So that is what Moore's law is about. So let me come from a slightly different world altogether, because the packaging that was discussed yesterday, and also the new areas of computing, not the conventional computing, but looking at learning and artificial learning as a tool to do computing is emerging reasonably well, and still all these things are done on a conventional computer. At the end of the day, the hardware is the same. But then we need to rethink the hardware itself. That is one part of the story. But then the other part is to look at whether we can augment the current hardware to do better, right? Is there any limitation in the current hardware that we can do, right? And then comes, how do we utilize the hardware, right? So the algorithms that you use on this, right? And how efficiently you can do computing. So there are different aspects that you can address to make computing much better. So I don't do software. I know nothing about software, right? So we are, down to earth device people, right? We push device to deliver what we want, right? When I say device, right, we are talking about when I move a photon from point A to point B, what is the kind of processing that I can do, right? And if I want to change the property of a photon, right, or electron, how do I do that, right? So that is where our expertise is. In the next, let's say about 28 minutes or 25 minutes or so, I'm going to talk about how we can utilize photonics for this, right? So light, basically photons for this, right? And what is the origin of this thinking process and where we are right now? You might think AI and ML is the thing, but then it is still running on a hardware that's reasonably old. And for us as a hardware person, you can call any name you want, but if it is still running on the same system, I don't see a huge jump in the performance, right, that you can achieve through this software iteration that you're looking at, right? So let me just share my screen and then we can start from there. So you can see my screen, I believe.
Yes. Maybe you can
Excellent.
start the presentation. Oh, yes, perfect.
Excellent. So those are all my coordinates. So if you want to get in touch with me, beyond this discussion, or if you disagree on some of the aspects, I would really love to have this discussion go forward. Okay, so let me start with this topic of, though the topic is the emergence of optical computing, right? In half an hour, it is difficult for me to say that optical computing has different phases, right? But let's start with this, what I used to call this, old dog, new tricks, right? So the whole dog here is, the photons are old dogs. And also the material that we are going to see here is also a very old dog. So we are going to use silicon, right? So silicon is the material with which we have built, all the electronics that we have today, right? The very reason you are able to see me on your screen is because of silicon. The way the reason why you could hear me is also because of silicon, right? If silicon was not there, then probably life would be very different. So how we are going to use the silicon technology, how we are going to use photons, right, in order to address this Moore's problem, right? And definitely, it's contributing to the fading law, right? And also there are different strategies how we can, mitigate the current scenario. So why we want to go to this chip scale, right? So we want to do everything on a chip, right? So that is how we think everything should be miniaturized, right? Scaled down, right? Everything need to be scaled down, starting from your mobile phones, for example, right? It used to be reasonably large, but you want to make it really, really compact. But now it is so compact that you can wear it as a watch, right? So watch is not watch anymore. It has various functionality. I don't know what to call, right? It shows you time. It takes all the biometric from you, right? You can make a call and you can receive a call. It's not specific anymore. It's multifunctional. The power of that is through integration. So how do we bring in bulk, processes, right? So bulk functionalities onto a thin substrate. So that is what, this whole chip concept is all about. So what is the purpose of this integration? Integration brings in functionality, right? So you can bring in a lot of functionalities, but then you can also enhance the performance, right? So by integrating this, you can improve the performance because you can avoid transition or transmission losses. So if you look at CMOS, I'm not sure how many of you are aware of this, have seen a concept like this. CMOS scaling, right? There are two types of scaling that has completely revolutionized microelectronics, right? One is downward scaling that we all know of. I think this is what we just saw, right? The 2.6 trillion transistors. So that is because we are constantly reducing the size of the transistors, right? We are constantly reducing the size over the years, right? And this is what you see, right? The first CMOS only came, in 80s, right? And from there on, right, consistently we started reducing the transistor size to put more transistor, right? And that is what we call economy of functionality. I want to have more functionality, right? But then the other thing that we are not very, much open about is upward scaling of the size of the wafers, right? Size of the platforms that we process these chips, right? So we have a rectangular or a square chip. That square chip comes from a very large, silicon wafer, right? And we have increased the size of these wafers consistently. And we have reached a point that there is no economy of scale beyond 300 millimeter, right? So 300 millimeter is 12 inches, right? So it's reasonably large, right? So there is an economy of upward scaling and downward scaling that actually propelled the microelectronics. Okay, so this is very important. And the other thing is, can we go down below this, right? Whether we can make even smaller. So 5 nanometer, 7 nanometer is now getting into production, right? And going beyond that, there is a physical limitation. Let's look at on the other side. Can I make it even bigger? Huge wafers, right? But then you lose the economy of scale, right? So I need to spend about 26 billion or 30 billion to put up a fabrication facility. If I go for even bigger, then this is business, right? I mean, from science point of view, you can talk about this, but it is business, right? I'm not going to put so much of money, right? That the return is going to be next 5 or 10 years. Just get the first wafer out. So that is the dilemma here. So there was a proposal to go to 420 millimeters, but this was dropped because the industry did not see any benefit or economic benefit in going to that large wafers. Okay, this is not solar cells, right? Meters and meters. So this is very different ball game altogether. So what this has brought, right? So we have gone from 45 nanometer footprint to 90 nanometer footprint. Let's say 90 nanometer to 45 nanometer. So I can fit in the same functionality what 90 nanometer was offering into a much smaller footprint. And what that has enabled is going from a single core processor to a multi-core processor. Today, I can have thousands of processors on a single die, right? Or a single wafer platform. I can have that. It is, physically it is possible. But then the question is it possible for me to use all those processors? Okay, it is similar to having, apartment blocks, right? That can house, let's say, 1,000 families, right? And then I give you one lift, right? To commute from ground floor till, let's say, I don't know, about 30 or 40 floors. If there is only one elevator lift available, then having 30,000 family housing is nonsense, right? So physically having resource is not enough. We need to make sure whether you can utilize that, right? In current day processors, you are talking about, I can have 8 core processor, 16 core processor, right? Whenever you are buying a laptop, you just go and look at the specification. Oh, this laptop, the processor has 12 cores with multi-threading, right? And the other one has 16 cores and so on. But look at the processing capacity, look at the performance benefit that you get from a 4 core to an 8 core to a 16 core. The increase is marginal. It won't be linear extrapolation. Okay, the reason for that is the processes are sitting there, but you should provide data to it. Okay, this is a traffic problem, right? People who are living in Bangalore and big cities, they all know, right? You don't measure distance between places by distance anymore. We have come up with a new unit. We measure it with time. Okay, how far are you staying? Right? It's not 5 kilometers. I'm 20 minutes from here. Oh, that means perhaps 2 kilometers from here. But that's how it is, right? So the traffic, how do you manage the data that you can give, process, and then take it back? And that is what we call the wiring problem. How do you connect these cores together? How do you connect, the logic or the core to the memory where you're storing the data and retrieving the data? The core is where all the, action happens, but then the core has very poor memory. It has to store it, and then it has to pull the data whenever we need. So there is a huge issue here, right? So this is what we call bandwidth bottleneck, right? How do we solve this problem? So we already solved this problem in a really huge macro scale. What you are looking at here is all the continents that are connected with this dots and red lines, right? This is nothing but submarine cables connecting the continents, right? And the very reason someone is sitting the other side of the globe can listen to me without any delay, right? And that is because of this connectivity, and just not connectivity, the speed of this connectivity. And this is all thanks to optical fibers, right? And optical fibers are just medium, right? And beyond that, what we have inside optical fibers, the photons are carrying the energy. Photons are carrying the signal, right? The fastest thing that we know today is photon. Okay, so we haven't come up with anything faster than this. There are few attempts to do that, but still photons are the fastest moving particles that we know. The idea is, can I take this whole network, compress it, and put it on a chip? As simple as that. I know the solution, but it exists in thousands of kilometer scale, but now I need to scale it down to centimeter. Can I do that? The first thing I need to understand is, how do I make the photons move around, right? So you have this optical fiber, right? And that is going to carry this energy. And basically what you need is a light guide, right? You need to guide the light where you want the signal to be routed. And there are lenses that we know, there are mirrors, right? So you can use mirrors to, as a kids, we have done this, all these fancy, playing with aligning mirrors and, putting your light from spot 1 to spot 2, right? And in the labs as well, right? But then those are all reasonably large, right? The concept that we use is called total internal reflection, right? So when you take a fiber, right, you put the light in, you need total internal reflection to keep the light inside the medium, right? So that is what takes the light form. So that is fine. I can keep the light inside, but now I'm talking about circuits, right? So can I make this on a chip or a circuit, right? And that is what these kind of strips and thin lines are going to do, right? So the thin lines that I make with the material that I call silicon can help you to confine, put the energy, and it can extrude in this direction, right? And then it can take the energy wherever you want. Okay, so these are the simulation that tells me that there is a possibility of confining the light in the space, right? And the next question you would ask is, okay, now you tell me that you can have these rectangular geometries to confine light, but then how small are these, right? So I want to know the size of this structure, right? And this comes from the density of the medium and also the wavelengths that you're going to use, right? And not going into the detail, right? The wavelength changes based on the material, right? And right now, if you're going to use the telecom wavelength, which is 1550, the wavelength of light inside the medium is only 450 nanometers, right? If you just want to have some relation, right, of this nanometer, right? A human hair, right? A human hair is approximately 100 micrometer. Okay, so that is what human hair is. So this guy, the wavelength is about 0.45 micrometer. They are rather small, right? That is what we need, because we want to put this on a electronic ICs, right, to see whether we can solve this problem, right, of what we call traffic, right? Because light is fast and we have a traffic problem. Can I solve this traffic problem with light, right? So I talked about silicon photonics. Why silicon, right? So silicon, because we already know about silicon, right? We know enough about silicon. We have been working with silicon for decades now. So there is a mature technology available, right? And this photonics is high speed, right? So you can do this deadly combination of technology and the functionality. So you can get the best out of these two, right? So that is what the silicon technology is going to bring. And the platform is very versatile, right? Because speed is key here. I can use it for high-speed interconnects. That is what I will shortly talk about. I can use for microwave signal processing, right? Communication, and also I can use it for sensing, right? So it's basically light. So light will interact with the medium, right? And you can use it for these multiple purposes. Okay. So I talked about this photonic integrated circuit, right? What do you need in order to realize a photonic integrated circuit? Right? You need all these components. You need a source, you need a detector, modulator, filters, and guiding medium, and so on, right? So all on a single chip. That is what we need. So the idea is to realize these chips, in an integrated fashion to support the electronics. So how are we going to get this electronics work for us, right? Or support this electronics? So the idea is to support the data transfer, right? So you have logic, you have memory. So how do you connect the logic and memory, right? By using this laser, right? Is the question here. So you can use what we call optical wire bonding so that you can connect these different electronic modules that they can communicate much faster, because connection between logic and memory is key. All right. And we have demonstrated these kind of waveguides, very small waveguides with reasonable propagation losses. Let me just scan through what one can look at, right? So you want to have a filter. I mean, filter here means different channels, right? So there are hundreds of cores, and each core wants to talk to some other, core in the circuit or a memory, right? So each one will have a channel, each one will have a color, and they can talk to each other, and you can filter each color out, right? So that then you need a filter to do that, right? And that is what you can do. And then the next thing is, how do you convert the electrical signal to optical signal, what we call modulator? Because electrical signal we know, but now you're talking about optical signal. So how do I map electrical signal to optical signal? And among the crowd, if there are some, electronic engineers or people who have done physics, we just do it with simple diode, right? PN junction diodes, right? And the diode allows us to push and pull the charges, and the light feels that. And here I show a device, right, which can operate at 25 gigahertz. And this is already very old result from us. So you can also get this for 50 gigahertz, one single device. And it can actually pump out 50 Gbps to 100 Gbps of the signal. So the massive amount of data can be pushed by using optical devices. And it is electrically connected. So if you want to transfer the data, I just connected electrical signal through this, right? There is very little amount of overhead here to convert electrical signal to optical signal, right? And the next thing is to have light sources, right? The moment I say light sources, what comes to your mind is lasers, big lasers and running around. We cannot put those big lasers on chip. Simply impossible. They are too heat generating, right? So here what we look at is it possible to generate multiple wavelengths on chip, right? And what you see here is there are 10 different wavelengths or 10 different channels we have created by using just 2. Okay, so you can have an off-chip power source. You put it into your chip like your SMPS that you have. You just generate more number of wavelengths inside the chip itself. This is all possible. And the next thing is detector. Okay, I can generate, I can filter out, right? I can modulate, but can I detect this, the photons? I want to convert the optical energy to electrical energy, but at the end of the day, everything should be electrical in nature. That is where photodetectors comes, right? And here you see again a much smaller scale photodetectors integrated on chip. And these detectors work, about 15 gigahertz, right? Without, sweating. So these are all very fundamental, working of these devices that we can exploit in order to do optical interconnects. The idea is to support the existing, logic and memory using these various components that I can attach with this existing electronics, right? All we need is to rethink about the architecture of integrating this. Let me just change gears here. We talked about how to improve the existing infrastructure, right? This is basically pushing what you have, right? So we have a huge infrastructure with electronics. How do I make it faster, right? Because it is just a traffic problem. But we have to think, radically here, right? Can we do neuromorphic, right? Neuromorphic is key because our brain doesn't use that much of power, to compute. All right. So we do all our brain does, or for that matter, brain in any living being does amazing work, right? Better than the processors that we do. The idea is, can we do neuromorphic computing? But neuromorphic computing, not in conventional hardware. Let's do it photons, because photons are fast. They can be parallel, and let's do that. So artificial intelligence through neuromorphic computing by using photons. I don't have to go through this. Probably you must have seen this in the workshop somewhere. Everything is moving towards this cognitive process, right? We don't use memory, right? You don't have a separate resource called memory. Memory is inbuilt, right? So what you call in-memory processing. So you want to have a storage, but the processing happens in the storage itself. And that is what brain is all about. So brain stores everything, but then the processing also happens wherever the information is stored, right? Can we think of an architecture beyond von Neumann architecture of having these different blocks in different places, right? And this fits well for photons because photons are bosons. Okay, they don't share energy. Unlike electrons, electrons are very, kind. If you want the electron to give some energy to another electron, it will, without asking questions, it will do it. But photons are, really notorious. It's very hard to work with photons. I mean, I really like them, but they are very notorious. They don't talk to each other. They don't share energy. But this perfectly works here because all these neurons, they work in isolation. They only interact through the synapse where you just trigger whenever necessary, right? So we can look at that current architecture that's being used, right, as a time division multiplex system, because in all your architecture we have traffic signals. You say stop, that guy need to use, and then once he is done, then you can do it. We don't want to do that. There is no waiting here at all, because the problem is I can't store photons. They are ridiculously fast, right? I cannot store them also, right? So I want to use that as an advantage, right? And then use what we call neuromorphic processing by integrating all the photonic functionalities that I talked about, right? All this modulation, filtering, all those are part of the network. And for example, the modulation that I talked about, right, is actually changing the phase or changing the state of light, right? But then in a global network, they will talk to a CMOS ASIC, a microcontroller, the memory, and all these things are attached to it, which is conventional missions, right? But then the heart of this processor is going to be photonic IC, right? So this is where things are moving towards. And I also hinted that, it's not just neuromorphic processing. People are trying to move towards what we call quantum computing as well, right? So there probably must have had a separate talk on quantum computing, but what we are trying to do here, right, with this architecture is not just quantum computing, but we do optical quantum computing. Quantum computing has its own advantages, but then using photons makes it even better, okay? And the beauty of this is I can use the same architecture that I built for neuromorphic processors. As simple as that. The architecture can be exactly the same, but instead of using a continuous wave laser, I will use a single photon. right? And then I will have a single photon detector, right? So this is the platform that people are moving towards, and there is a lot more one can do with these kind of dynamically programmable neuromorphic processors. I think I will stop here, and I think we can have discussion on these kind of evolutionary and also revolutionary ideas that are coming up that are related to photonics. Yeah, I think I will stop here. Yeah. Thank you. Because I think I've gone over time already.
No, there's time still left. We can start the discussion. if
That's
you
okay.
like.
Yeah, good.
Okay. That was an amazing talk. And I really liked how simply you put it, like not being able to use the resources because of the traffic. Then, of course, the silicon photonics. Why do we even delve into that? And then finally, that neuromorphic computing in photons. We do have a couple of questions for you, if it's okay, please.
Absolutely. Let me just have the chat box opened up. All right.
So I think you'd rather like to open the Q&A tab rather than the chat
Yes,
box.
not this one. Yes. Aha, it's a much more a technical question. I try to keep the technical details to very minimum. Just don't want to make people sleep. Okay, I'll take that. So insertion loss and crosstalk, very, very, very important question. Let me, for people who are not from the field, let me just give you a briefer on that, right? So whenever you talk about any photonic process, right? Any process. It can be any process. Forget about the process. If you need to give an input and there will be an output, right? So the input will have a certain number of photons, right? Let's say this is photon number, right? And the photon number can be of some kind, right? So this is the distribution of photon number, and the output that you get will be reduced than what you have as the input, right? So this is the output. So this difference, right, what you have is called insertion loss, right? So that means how much of energy that you lose going through a particular processing stage, right? And that is what we call insertion loss. So this has a direct implication on the power requirement, right? And for that's one of the reasons why we want photonic ICs to have all the components integrated, because the moment you go from one chip to the other chip, it leads to loss. Because unlike electrons, where you just touch a wire, you have electron flow, right? It's a lowest resistant path. But that's not the case with photons, because the wavelengths of photons are reasonably large compared to electrons. So the light will feel the shape and the topography of the circuit or the object. Okay, so whenever it interacts with any object, some of it will go through it and some of it will be reflected as well. Okay, so this is the nature of any optical element. So you will have transmission, you will also have reflection. So these are our primary loss mechanism. And then you will also have something called resistance to the flow, right? That is called loss, right? So resistance to the flow could be scattering of the light, loss of light. And this is what insertion loss is all about. You want this insertion loss to be zero, as an idealist, right? You want zero, but then you can't have it. I mean, life is hard. So what you want to do is you want to do this calculation, right? From input to an output, you will have multiple stages where you go through, right? And then do what we call the power budgeting, right? You do the power budgeting, and then you can say like, okay, I can only afford 5 dB of loss, right? And then you have to improve the efficiency of this couplers, or rather the stages that are connected with each other, to have very minimal loss, right? So I want to have 1 dB, and then I will still be 3 dB, which is less than 5 dB. So this is how we work out the solution for having this power budgeting of insertion loss. The crosstalk is more about, I will go back to that to this particular graph, where you can see, the crosstalk is between two different channels, right? So I have channel 1 and I have channel 2. So they are isolated here, but if you look at here, channel 1, you can see some leak from channel 2 can go into channel 1, and this is what we call crosstalk. And here the crosstalk is about 20 dB, right, which is large enough. 15 dB is good enough for any decent system. So this is what crosstalk is all about. So if you want to have a better system, you want to have large crosstalk margin and very low insertion loss, right? Very good question about thermal effects, right? I think Kanchan Manna knows quite a lot of things about photonics, I think, in the circuits. So here you can see the effect of temperature. Basically, the power here is thermal, right? So the shift here, right, is about, I would say, 0.1 nanometer per 10 degrees C. So when the chip heats up, your devices are going to move in their response, right? So thermo optics, what you call the change in the refractive index as a function of temperature, right? So this is non-zero, right? That means with temperature change, your refractive index is going to change. That means optical density is going to change, and that will move these responses. And there are ways to have this DNDT 0, right? What we call athermal devices. So that should be. Okay, so let me think, how Moore's law can be defeated by neuromorphic computing? Well, it's a philosophical question. I mean, well, how do you define Moore's law? I mean, if I'm not from any school of thought, okay, as a neutral person, Moore's law in its strict sense is talking about increase in the number of transistors, as a function of time, right? But then we morph that to functionality or performance evolution as a function of time. Okay, if I'm going to stick to that performance metric, that neuromorphic is actually going to add, right? It will not defeat. It's going to add more functionality, make it more performance than what you can get out of the systems now. Okay, so that's what kind of application can be used can be used by using photonics neuromorphic? I'm aware that they said ML, but just want to know about the specific names of data sets if you have tried. Also, I would like to know that can be FPGA to be used for driving. Excellent. Very nice question. Thanks for that, Mr. Shah. Let me take the first question on neuromorphic and photonics, right? So neuromorphic is a concept, right? You can do it in multiple ways. So we are picking photonics as a platform to implement this neuromorphic. And the very reason neuromorphic is much easier to do, or rather, let's say, no, I should not say easier, very comfortable architecture is it's very flexible, right? I don't have to operate with the hardware that I have or the architecture that I have. So it is an evolving, architecture. So that makes life much easier, right? So what are all the applications that I can use this, right? One of the applications that people already have tried and demonstrated is on classification problems, right? So the classification problems that you can run on photonic neuromorphic platform is orders of magnitude faster than what you can do with regular electronic implementation, Okay, so optimization problems are very much the target of this neuromorphic platform. So ML and AI are basically the algorithms. You can implement those algorithms using the neuromorphic architecture that you're going to build. And the next question is about FPGAs, right? Because that is, if you are a architecture guy, you love to have FPGA, so you have this flexibility, right? In photonics, the neuromorphic computing, photonic neuromorphic computing is basically a photonic FPGA, because there you need to dynamically program, the components or individual components or individual circuit elements. So if you can, you can find it in a lot of literature. There is photonic, or what we call programmable photonic circuits, right? So that falls under the category of optical FPGAs. Right? In prototyping the optical computing, yeah. So the prototyping, the optical computing can be done with this programmable FPGAs that I was talking about. Okay. Can we have a complete optical processor avoiding electronic processing in future? Absolutely. Everyone would love to do that, but then there are differences. Okay, as I said, it is impossible to replace the current electronic processing. Okay, because of the fundamental nature of optical process and electronic process. As I mentioned, optical processing can be done, or rather, you need to actually qualify the statement of processing, right? We loosely use this word processing. There are different types of processing, right? When you talk about classification problems, right, you don't need to do a lot of computation. What I say, arithmetics is minimal. Okay, wherever arithmetics are involved, right, there you need to have a lot of feedback paths and optimization paths that are required, where energy needs to be shared between modules, okay, and between signals as well. If you ask me a fundamental question that whether a complete electronic process can be implemented by optical process, the answer is true. We can do that completely. We can do that, but it won't be energy efficient. The energy required to do a full optical processing would be unimaginably higher than what you can do with electronic processing. As a fundamental question, yes, you can do that, but it won't be energy efficient and it won't be scalable as well, because you need, thousands or millions of gates, right? But having that kind of scaling with optical circuit, with all these power requirements, it's going to be just a hero experiment, and we write a cool science paper about it and we become famous, and that's the end of the story. Nothing is going to happen beyond that. No one is going to pick up and make a living out of it. Okay, so yeah, that's a problem. It is photonics is good for certain things, optics are good for certain things, but you have to use it wisely. If you go optical fascist, life is very short.
Maybe one quick question from my side. How do
Yeah.
you see the timeline of those evolutions? I mean, when will these things get out of the research area, and maybe are there certain domains where you think these will first be applied?
Good question. I think let me start from different technologies and then see where they are right now. The first thing is on this interconnect, right? So interconnect problem, with silicon photonics and other platforms that people are thinking about. It's already in the production right now. So it won't be long that not your laptop, perhaps your servers will have uh, uh, you know, sockets that can accommodate, optoelectronic processors. Okay, so it will be very transparent. So you don't have to worry about it at all. The only thing that you will see is it has become ridiculously fast. And from there on, it's just a matter of time for it to enter your laptop. Right now, we are comfortable with the processing that we have, but once the commodity comes in, and it should be there. The reason why I say that is there are production lots already running, and it should be soon, out on the racks. Okay, so that's the first product, as you say. But the optical interconnect for data centers, right? Even if you go today to your data center, those are all already with this photonic ICs. There is you can go and buy it off the shelf. That has photonic ICs already, that you can plug your SFQ or QSFP modules just into your racks. So those products are there. So the other technology that I talked about, right, the neuromorphic quantum computing, optical quantum computing, those are all just emerging right now. We are solving some fundamental problems, right? Like what I said, it is very difficult to store photons. We need to come up with the architecture that, I can live with very minimal amount of the storage time, right? So that I can realize these circuits. And how do I switch the states? And there are some fundamental problems that people are solving right now. And there are already startups on this photonic neuromorphic computing. So that means people are actually very positive about this technology and commercial viability of this technology. And probably, I think in next 5 years or so, we should have this technology argument, whatever we are right now doing. On the quantum front, I think there is a race on different fronts. When we say quantum optics, lab scale or table scale experiments are working excellently fine. Okay, but then how do you create a computer that I can put in a server room, for example, right? So in the form of a chip, which are energy efficient, I don't need 100 lasers pointing to a mount and so on. Instead of that, can I have a much better solution to that? So there are some technical challenges and also some fundamental challenges being addressed. There again, I think 5 to 10 years would be the quantum computing timeline on the photonics hardware, I would say. So this is roughly the timeline as per my understanding so far.
Thank you so much. I also think now the time is almost up. Especially thank you. I mean, this is by far not my area of expertise. Thank you for explaining such a complicated topic in such an approachable way that I really enjoyed that a lot.
Appreciate that. No, I think I just want to keep it low. Just because one of the easiest thing for me to do is go to the details and make you sleep, right? Right? But that's not the purpose of this. ThoughtWorks. So it should evoke thoughts, right? Not just go to sleep.
I don't think anybody fell asleep.